The buck converter uses switching mechanism to convert high voltage into low voltage, and hence it generates a lot of electromagnetic interference. To reduce this, we need a filter. In this video, we are going to talk about when to use network simulation for filter design. Hello, my name is Bibhu. I am a senior researcher at Graz University of Technology. Today, we are going to talk about how the spice level simulations are used to optimize this filter in our work. As we have talked before, we can see here this is a buck converter. It has multiple switches, high side and low side, and the switching noise travel from the buck converter through the harness to other device or the battery. In this case, we can see the switching event happening and the noise we can see in the diagram. So our aim is to suppress this noise, and hence we need a filter. Now to derive the right value, we can do in two ways. Either first we start with the design and we have a prototype and we do a measurement. Once we do the measurement, we can optimize the filter. This takes a lot of iteration. We need to fabricate each time. The other way around is that we make a simulation. We optimize the values of the component through the simulation. That way, we save a lot of time and money. So now let's talk about how the simulation is performed. Either you can do a circuit level simulation or you can do a full wave or field simulation. Each has their advantage and disadvantage. The basic governing equation of this circuit simulation is a well-known Kirchhoff current law or voltage law. Signal propagates from one node to the other node instantaneously when our structure is electrically small. That means it's very negligible in compared to the wavelength. Or we say that the parasitic impact of the layout of the structure is minimal. Other way is when the structure become electrically large, or we see there is a lot of impact of the parasitics. We need a field solver which uses the Maxwell equation in the background to solve basically field quantities. And in that way, it considered all the parasitic. But the disadvantage of the full wave solver is that it takes a lot of time and a lot of computational resource. In this video, we are focusing mostly on how the spice level simulation is used and when we can use the network simulation in our design. Now let's start to understand what is the criteria where our transition happened from network level simulation to full wave simulation. In this example, we have a 10 ohm resistor mounted on the PCB. Now we want to extract this impedance of this trace, which is terminated with the 10 ohm resistance over the frequency. As we model this in our spice level simulation, we have a 10 ohm resistor, we have a current source, we have the parasitic extracted from the traces approximated to some inductor and the capacitor. And when we extract the impedance over the frequency up to 10 megahertz, our impedance is constant. As we move higher in frequency, we see the impedance value changes from 10 ohm. That means the parasitics has an impact now. At very low frequency, inductor is short and capacitor is open. As you go in frequency, the frequency dependent behavior comes into picture. That's why we see a different impedance value. So for our analysis, we can see as long as we see the impact of the parasitic is low, we can use our network simulation to alter or optimize our design. By understanding this, let's start to our filter simulation. Our filter consists of a differential capacitor called Cx and the Cy capacitor and also a inductor. This component also have their frequency dependent behavior. Now let's do a simulation. We can see here the two circuit. One where we have all the components are modeled according to the parasitics, like in this case the choke, the Cx and Cy, and this is the case where we have the ideal component. And this is the case where we don't have any filter component. And we see here when there is no filter, which is the red plot, we see constant 1 volt over the frequency. Blue line is the voltage when we have ideal component, and the green line is the voltage when we have model the component with their parasitic. We can clearly see once we have the parasitic value in the component, the voltage is quite different from when we have an ideal component. That shows that in spice level simulation, we need to consider the parasitic impact of each component. And now we'll see the field simulation. In this case, we have used CST for our field simulation. This is the filter structure. You can see this is the plus and minus line. We have a Cx capacitor here and the choke here and two Cy capacitor here. We'll extract this parasitic behavior of this filter using CST. The extracted parasitic of the traces along with the component have been attached to the schematic. Now let's compare the filter performance. The blue one when you have a spice level or network level simulation, the orange one when you have a full wave simulation. Again we can see there is a good correlation between spice and the full wave simulation till 1 megahertz around. And after that, there is a huge difference between full wave simulation and the spice simulation. Understanding the filter simulation and when to use the network simulation, when to use the field level simulation. Now let's check what is the impact of the filter on our emission of the buck converter. This is a buck converter circuit which we have seen before. This is the switching noise which is going out of the duty. Now once I have put the filter, we can see our noise has come down as in shown in the green line. It has come down drastically. So this shows us that we need to optimize the filter, we need to find the correct value and we need to find the topology. What we can conclude that we can use the network level simulation as long as the parasitics are very minimal. When our structure is electrically small, we can still use the spice level simulation to optimize our filter value or optimize our design. This is much faster than the full wave simulation. As we go to higher frequency, the impact of the parasitic becomes dominant, and that point we need to switch from the network level simulation to the full wave simulation. Thank you.